This is part 1 of the second lecture of week 9, where we discuss inverse Laplace transform. And firstly, we come to the question, why do we need this Laplace transform, together with the question, why do we need this inverse Laplace transform? So, Laplace transform together with inverse Laplace transform will help us to solve some initial value problems. Let's see how it works. Consider the following initial value problem. This is equation y second derivative minus y equals to minus t together with initial values and let's see how we can solve it using Laplace transform. The first thing, we apply Laplace transform to the both sides of the equation. So we apply Laplace transform to the both sides. And these two must be equal because we have equality for functions. Using the linearity of Laplace transform, we can write that this is Laplace transform of the second derivative at a point s minus Laplace transform of the function at a point s is equal to minus Laplace transform of the function t at a point s. And sorry, it's not enough space for this, at a point s. And now we know the Laplace transform of second derivative. Laplace transform of second derivative at a point s from the first lecture. This is s squared times Laplace transform of the function at the point s minus s times function at 0 minus the first derivative at 0. Or these two are given, right? These are initial values. We can write this as s squared times Laplace transform of y at s. Y of 0, this is 0. Y prime of 0, this is 1. So we got minus 1. And let's replace this Laplace transform of second derivative in this equation by this expression. What do we obtain? Laplace transform of the function at a point s minus 1 minus Laplace transform of a function at a point s is equal to minus Laplace transform. And here we know that Laplace transform of a function t is 1 over s squared, right? So just replace it. And from this we can find Laplace transform of y at a point s. Okay, we can move this 1 to the right side. We obtain 1 minus 1 over s squared and simplify all this stuff. We obtain overall 1 over s squared. So you can check this. And now we need to find y, right? And we know that Laplace transform of y is equal to 1 over s squared. So for which function y this is true? So we know that Laplace transform of the function t at a point s is 1 over s squared, right? So it's reasonable to say that y equals t is solution. So you can in fact check this fact. You can just substitute this function into the equation and you will see that indeed this is solution of this equation. And this step here, at this step here, what we did, we kind of made the inverse operation. From 1 over s squared we come back to t, right? So here we make the inverse operation or inverse mapping to the Laplace transform. So here we need the inverse Laplace transform. But before introducing definition of inverse Laplace transform, let's also think about the following fact. Is it y equals t the only function for which Laplace transform of this function is 1 over s squared? In fact, this is not. For example, if we consider function g, which is differ from function t just by 1 point, let's say g is t when t is not, let's say 6, whatever, and g is 0 when t is 6. Then you can check that since Laplace transform is integrable operator, 1 point is not so matter for the result. So Laplace transform of the function j at the point s is also 1 over s squared. And there are plenty of such functions. Any function which is differ from the function t by in just a finite number of points will give Laplace transform 1 over s squared. So there are many of such functions. Which give Laplace transform of them at the point s is 1 over s squared. So which function we will call the inverse Laplace transform, and which function we should choose when we solve differential equations like this? Let me write you the following result. So among the functions, say functions g, among the functions g, such that Laplace transform of the function g at the point s is 1 over s squared, the only one function is continuous. Exactly, the function g of t is just t. And this continuous function we will call inverse Laplace transform. So let's introduce now the definition of the inverse Laplace transform for a given f of s if there is continuous function f, such a continuous function on the semi-interval, such that the Laplace transform of a function f is exactly capital F, then the function f is called inverse Laplace transform, and the backward operation is denoted, f is denoted L minus 1 of the function f. So you have to remember that it must be continuous function in the definition of inverse Laplace transform. We'll consider some examples in next video.